Happy Friday, everyone. Rabi from RKALC. We are talking today about a masonry application under the sidebar there. It is very important and productive web app that can gets you with the compression capacity, bending capacity, shear, as well as fire capacity of the wall for the typical day-to-day block work that you see every day in the industry. The wall in question is one linear wall that is 2.8 meter high, and the block work is 190 thick. And there you can find whatever the desired block unit that you see in the industry. It will be there in the drop menu. We will work out, first of all, the compression capacity, the bending capacity, shear capacity, and fire. Before I go into the example itself, this is part of the verification project. You will see a new item there on the sidebar that is for RKALC verifications. For example, we've just published verification examples for FECalc, and we will be rolling out more verification casks. So if you would like to participate in this verification project by the community, please message me directly on LinkedIn or through email, and I can provide you with 2 weeks free membership just to do this one. Back to the masonry application or the example there, we will need to work out the compression capacity, which is related to the slenderness of the element itself and the properties of the materials that we are using. The bending, the section capacity, which is F naught, it is having like two components. First of all is the shell or the block itself capacity plus the grouting capacity. And there you sum them together, multiply them by fire reduction factor, and then multiply this number by slenderness reduction factor to get the member capacity. So that is what we are having in this calculation. But before that, you need to, I wanted to start with the compression capacity calcs, but before that, because you need to know all of those things, you go to the first page, which is going to be published very soon. Establish the type of the block work, what is the bedding type, the grout MPA that is inside of the block work. The example we are resolving there is unreinforced core-filled block work. You've got the mortar is M3, which is the glue connects the block works together, and FUC is the complete capacity of the block unit itself. FY is not important because this is non-reinforced. Now, if you go to table 3.1 and you put all of those, you select all of those items, you will end up getting the F prime MB, which is the characteristic compressive strength of the masonry. You multiply it by this number, you get the design capacity of the block work wall, essentially. KC is a factor for the masonry type. You can get it from the standard. KH is a factor that relates to the thickness of the bedding. Phi is the strength reduction factor depending on where the block work is working. So we will be adopting 0.6 in this example. KT is a factor relates to piers. So if the wall has piers, to make it work like two-way action kind of. So if you've got piers spaced at 6 meters or whatever, so the wall works in two directions, so you get more efficiencies on the slenderness. But I'm not gonna use this in the example, although it is available for you to work it out. Alpha is factor relates to the fixity between the ends, so I'm gonna take one in this example. We'll nominate 10 millimeter eccentricity. SRS is the slenderness of the wall, which is h divided by the thickness, height of the wall divided by thickness, multiplied by the fixity factor on ends, and a KT factor, which is a reduction factor for slenderness that can be taken from this table. So when we work out this formula there, we will get, first of all, the shell capacity, which is AB, the block skin itself, times the capacity of the block, and you add it to the core capacity of. So you've got the block looking like that. So AB is this one, and AG is the one in the middle. So this plus that gives you the section capacity, and then you multiply it by a reduction factor for the slenderness, so you get the member capacity altogether. So that is ticked off there. By the way, AB and AG, you can get them from the application there. So what is the AB, what is the AG as a proportion of the block work? In this very example, you've got 52 solid area and 48 is the hollow area that we will fill with the grout being 20 MPa. And then you go to flexural capacity. So you've got, it's essentially the section modulus multiplied by the stress, nothing more simple than that. And then you've got a factor that relates to the actual compression stress on the block work. So the more compression you get, the more flexural capacity you get, essentially, if the eccentricity is not very high. So you work out this to get the minimum of these two. Work out all of that. Just know that the stress FD, so there you got FD times Z, and the tension capacity or like the rupture capacity multiplied by Z. That is one component, or this one. Rupture capacity is nothing but 0.2. You can get it from this close. Z is the section modulus, which is width times height squared divided by 2. And then you get MCV, which is the minimum of these two numbers, as I mentioned there. So you'll get 0.92 for the bending capacity. Shear capacity counts as well. Trace it in the standard. You need to work out the FMS, which is 1.25 times MT, the number that we got on the previous page. So you get it there. It has to be less than 0.35, more than 0.15. And then the shear capacity is a sum of two things, V0 and V1. V0 is the shear capacity relates to the block work itself, and then the friction components. Sum them together, so you get the member capacity on shear. Fire design, you need to work out the slenderness under fire, which is different from the slenderness under compression. So you've got a concession there, you can reduce to 0.75, so it becomes 11. So you just nominate your block work. So that is your block work there. And then you get what is the slenderness. So our slenderness is 11, so it is less than this number. And that is the type of the block works. Excuse, the highlight should have been down there. And then you establish the adequacy being 240. Insulation, it has something to do with the thickness of the material. So our wall is 190 more than 180, so you get 240. And that's all about it. And then if you're looking at RKALC, you just put all of those inputs exactly like we have started this example, and then you get all of the outputs exactly matching with what we have in the hand calculations. This serves again as a verification example for the this application. Again, if you need to participate in this grassroots verification campaign, please reach out. Thank you very much.